Hello. In this video, we're going to continue looking at the integral test. We will, in particular, consider how the integral test implies convergence for an infinite series. If you have not seen integral test number 1, the video previous to this, you should go back and watch that one first, since a lot of the themes in that video are going to be used here. Let's start by reviewing the integral test. The integral test says the following. Let summation k equals 1 to infinity a sub k be an infinite series of positive decreasing terms. That is, the ak's are bigger than 0, and a1 is least as big as a2, least as big as a3, etc. We also assume we can find a function f of x that is positive, continuous, and decreasing, and defined on the interval from 1 to infinity, and such that the ak's are given by simply replacing x by k and f of x. So the ak's are f of k's. And so really all that means is that the series summation k equals 1 to infinity a sub k could be written as a summation k equals 1 to infinity f of k. And usually whatever you see here behind the sum will do for the function f of k. Just replace the k's by x's. The conclusion of the test says this. Once you have all this in place, have that function f, you're convinced satisfies necessary hypotheses, that then the infinite series, summation k equals 1 to infinity a sub k, and the improper integral 1 to infinity f of x dx, either both converge or both diverge. So this result says that if we can find a function f of x, as described above, that relates to the series, the convergence and divergence will be determined by looking at the convergence or divergence of the improper integral. And we will, as we saw in the last video, in the case where the integral test leads to divergence, we were able to show that the sum of the series was at least as big as the improper integral. Today in this video, we'll look at an example concerning convergence, and we'll see that in the case of convergence, we're more concerned with this inequality, which gives us an upper bound on the value of the sum. So as our example, let's take a look at a fixed number p bigger than 1, and we'll look at the infinite series summation k equals 1 to infinity 1 over k a sub k. We'll show that no matter what the p is, as long as it's bigger than 1, that this series converges. A series like this, by the way, is called a p-series. We'll say a bit more about them later on in this video. So the terms of this series are generated by the function f of x given by 1 over x to the p. And you can mentally check probably that this function is positive and continuous. So we're never dividing by 0 for x is bigger than or equal to 1, and is decreasing on this interval. And finally, if you replace x by k in the function formula, you get 1 over k to the p, which of course is just a sub k. And as we saw in the last video, sometimes it's enough to check the decreasingness of f just by looking at the graph. So here's what the graph of 1 over x to the p looks like for x equal to 1. And remember here, the number p is a fixed number greater than 1 in this particular example. So to determine the convergence or divergence of the series, we can look at the convergence or divergence of the improper integral that we see here. Integral from 1 to infinity f of x dx, or integral from 1 to infinity 1 over x to the p dx. Now, when we studied improper integrals, we looked at this particular integral. We saw that it converged if p is bigger than 1 and diverges if p is less than or equal to 1. We are assuming p bigger than 1 in this example, so the integral converges in this case. Let's go ahead and review how we came up with that. In particular, going back to the definition of improper integral, the integral from 1 to infinity 1 over x to the p dp is found by doing the finite integral from 1 to b of 1 over x to the p or x to the minus p dx, and then taking the limit as b goes to infinity. And this is just a power of x, integrate with respect to x, so we can integrate that rather easily to get x to the minus p plus 1 over minus p plus 1. and then the limits on the integral from 1 to b. So next we put in the upper limits of b and 1, and the upper limit b gives us this term, and the lower limit 1 leads to this one. And the important thing to consider here, here's where the p bigger than 1 becomes important. If p is bigger than 1, that implies that p minus 1 is positive. And so this exponent down here is a positive exponent. So as b goes to infinity, that denominator gets very, very big and tends to 0, as we see here. And then we're left with just the other term, minus 1 over p minus 1, or 1 over p minus 1 as the value of the integral. So this integral, this improper integral, converges to 1 over p minus 1. And because the improper integral converges, we know that the infinite series converges by the integral test. So as I mentioned, this series is often referred to as a p-series. We see that term here again. P-series are going to be very, very important in the rest of this chapter. There are very, very important series for the comparison tests. We've talked about the case p equals 1 first, and the series converges if p is bigger than 1. You can also show by the integral test, and you should do this, try this. You can show that the series diverges if p is less than or equal to 1. Now let's see a little bit about why this works. So we're going to look at a picture similar to the one we did in the first video on the integral test. So once again, our blue graph here is the graph of the function f of x. So that's right here. There's the graph of f of x equals 1 over x to the p. And then below the curve, we see these red rectangles. For example, as it says here, the kth rectangle goes from k minus 1 to k. It's right here. That's the base. And the height of that rectangle is determined by a right endpoint. And so these rectangles, notice, all lie under the graph. Okay. Now, it turns out each of those rectangles, again, has area equal to a term of the series. So let's take a look at this point here. It has x-coordinate 1, and so has y-coordinate f of 1, which is the first term a sub 1, or 1 over 1 to the p. The next rectangle has base from 1 to 2, and this point up here has y-coordinate 2, and so this is the point 2f of 2, which is 2a sub 2, or 2 times 1, 2 comma 1 over 2 to the p, and so forth. So because these rectangles all have base of width 1, we can get their area just by multiplying by the heights. So the area of the first is a1, this rectangle has area a2, a3, a4, etc. And this last rectangle has area a sub n. So once again, the rectangles have area equal to terms of the series. Okay, let's continue with this then. So from this we see that the partial sum s sub n of the series satisfies summation 1 to n a sub k. We're going to break off the a sub 1 because notice the a sub 1 rectangle is out here, not really under this graph. So we're going to write this as a sub 1, and then to get the rest of the terms, sum k equals 2 to infinity a sub k. This is equal to the area of the red rectangle, the sum of that area, and this in turn is less than a1. We're going to keep that out here. And then we notice these rectangles from a2, a3, etc. They're all under the curve. And so that's going to be less than the area under the graph from 1 to n. So again, the a1 stays out in front, and then the series from 2 to n, the sum from 2 to n, a sub k, is less than the area under the graph as we see from this picture. So that leads us to the following, that s sub n, which is a1 plus the sum k equals 2 to n a sub k. And remember, a sub 1 is 1 over 1 to the p in this example, and a sub k is 1 over k to the p. And this is less than, here is a1 again, and here is the area under the graph, where x is between 1 and n. If we let n go to infinity through this inequality, we find that the sum of the series k equals 1 to infinity, 1 over k to the p, which is the limit of the partial sums, is no bigger than the limit of the integrals. And this gives us 1 plus the improper integral, 1 to infinity, 1 over x to the p dp. And again, because this integral is finite, as we saw earlier, that means this sum is finite, that is, it converges. So convergence of this improper integral, being finite, means the sum which has a lesser value is also convergent. Again, just note, here's why the decreasingness of f is so important and the decreasingness of the a sub k's. The decreasingness means if I use right endpoints for rectangle heights, as we did here, those rectangles are all going to lie under the graph, and that's what makes this inequality possible. So we're going to see how we can use these rectangle pictures to say a little bit about error and approximations. So let's take a look at the infinite series summation k equals 1 to infinity, 1 over k cubed. So we just looked at an example with this. We now have the case p equals 3 in the previous example, that p equals 3 is bigger than 1, and so we know this series converges. It's a p series with p bigger than 1 for that exponent. The partial sum s sub n, of course, is given by sum k equals 1 to n, 1 over k cubed. The goal is this. We want to find a capital N so that this partial sum, if we add those up, is within 1/1,000,000th of the true value of the infinite series. So it turns out that nobody knows exactly what the sum of this series is. Mathematicians, in fact, have worked on this for years, but no one knows yet what the actual sum is. So if you want to say something about the sum, you probably have to approximate it. One way to approximate sums is by taking partial sums and taking a large partial sum so that the s sub n is very close to the limit of the partial sum sequence, which of course is the sum of the series. So the purpose of this example is to see how we can approximate the sum of a series using a partial sum, and more particularly what we can say about the error in such a sum. We'll see how example 1 plays into that. So if we use a partial sum to approximate the true sum of the series, all that means is this. Let's suppose the infinite series has some sum s. That's it. And we're going to approximate that by this number s sub n up here. So our error will be the difference between s and s sub n. Usually we talk about absolute error, so we'll put that in absolute values, although it should be clear that s sub n is less than s. So this works out to be, here's capital S, there's the sum of the series from 1 to infinity, here's the partial sum, and if I subtract that partial sum from the complete series, all that's left are the terms from n plus 1 to infinity of 1 over k cubed. So this is the error in our approximation. Now, how big is that? Well, that's where the rectangle pictures help us. Now, we want this error to be less than 10 to the minus 6, so what we're going to do is take a look at this sum and see how big does n have to be to make that sum less than 1/1,000,000th. So this is what we want. What should the n be so that this inequality is true? So we're going to see how the rectangle picture helps us come up with the value of n by, again, working with an improper integral. So here's our picture. The blue curve here is the graph of 1 over x cubed. That's the function associated with the infinite series. And each red rectangle is a term of the series summation k equals n plus 1 to infinity, 1 over k cubed. So just as in the previous example, we have used right endpoints to determine heights of these rectangles. So the first rectangle has width 1, height here is going to be 1 over n plus 1 cubed. And notice that rectangle lies under the graph, and because this graph is decreasing, all these rectangles determined by right endpoints are going to lie under the graph. So what that tells us is that this error sum is equal to the sum of the infinitely many red rectangle areas, and that sum is less than the area under the graph of y equals x cubed for n out to infinity. In other words, the error sum is no bigger than the integral from n to infinity 1 over n cubed dx. Now, this last is a very easy improper integral. Should work through this, but you should be able to get 1 over n squared for the answer for that integral. And now, again, remember we want to make this sum, this error, less than 10 to the minus sixth. And because of the way this inequality runs, we're instead going to say, well, if we can make this thing less than 10 to the minus sixth, then the error sum is less than 10 to the minus sixth. So we're going to focus on solving this inequality. And that's very easy to do, as we see here. So this error sum will be less than 1/1,000,000th, provided we can show that 1 over 2n squared is less than 1/1,000,000th. And this is an easy inequality to solve. It turns out that the n would have to be something bigger than about 707.1. So perhaps we could just take n equals 708. So if you're curious about the sum of this convergent infinite series, summation k equals 1 to infinity 1 over k cubed, then you can say, well, I don't know what the value is, but it's approximately equal to that finite sum. And a calculator will quickly tell you that's about 1.20205591. And someone asks you, well, how good is that estimate? Well, you can say that is within 1/1,000,000th of the actual sum of that series. Pretty cool, huh? Okay, things to remember from this video. In this video and the last one, we talked a little about the so-called p-series. A p-series is a sum of the form summation k equals 1 to infinity 1 over k to the p, where p is a fixed number. So two examples of this are if p equals 10, we'd have sums of reciprocals of 10th powers, and if p equals 1/2, we'll have sums of reciprocals of square roots. And then you really just want to memorize this, I suppose, but it turns out that a p-series converges if p is bigger than 1, and it diverges to plus infinity if p is less than or equal to 1. These series are going to show up a lot, so you really want to have these facts at your fingertips to be able to use them quite quickly. And we saw that if we have an infinite series, summation k equals infinity a sub k that converges by the integral test, then, as we saw following the last example, we can use the integral test to estimate the error if we approximate the sum of the series by a partial sum of the series. And again, this is something you'll be asked to do in some future exercises and perhaps on exams. So do some practice with the integral test. It's a good way to brush up on your integration skills, review improper integrals, and we'll see you in the next video. Bye.